Hello everyone. We already have studied the transport and continuity equation in the last lecture. We have seen these equations under equilibrium and under steady state. As I mentioned in the last lecture that now slowly we are going towards device analysis. So majorly we will study three different devices, PN junction diode, BJT bipolar junction transistor, metal oxide semiconductor capacitor and metal oxide semiconductor field effect transistor. So technically there are four devices. However, metal oxide semiconductor capacitor will cover some of the concepts that we need to understand metal oxide semiconductor field effect transistor. Overall there are four devices. However, concept wise MOS capacitor, MOSFET, some concepts are overlapping. Nevertheless, we already have studied basic concepts related to semiconductor physics in the previous lectures. We are now almost in the middle of the course, and we should now start revising some of the concepts from the previous lectures. Just in case if you find any difficulty to understand a particular concept which has been discussed in the previous lecture, you can go back and check that. Now in today's lecture, we will start with approximations of device analysis. When I say approximation for device analysis, that means we will discuss some of the approximations with respect to device analysis. However, we also have discussed some approximations as of now as a part of carrier concentration, as a part of excess carrier, as a part of transport, so on and so forth. And I already have mentioned multiple times three very important approximation which one should remember, because these are conceptual understanding, and you may need to rethink about an analysis if the situation is not coming under that particular approximation. The first approximation, very important, is known as Boltzmann approximation, and we have studied Boltzmann approximation already, and it has some criteria. When you take Boltzmann approximation, you have to follow some criteria. But as I've said multiple times, that we are studying currently electronic devices which mostly will follow these approximations, but when it comes to sensors, which is not conventional. So usually the devices that we will study here are conventional devices. For example, PN junction diode is a conventional device. It's a silicon based device so far. Maybe there are many other semiconductor materials are used to develop PN junction diode, but mostly I am saying as of now PN junction diode is a silicon device. Bipolar junction transistor, again a silicon device. And the discussion that we will do here, considering silicon as semiconductor material, if not mentioned otherwise. And secondly, the MOS capacitor and MOSFET, they are also silicon based devices. So those approximations will hold good when we discuss the traditional devices, when we discuss the conventional devices, and when we discuss the conventional application. However, when it comes to sensors, probably these conventional framework may not be the case. This may not be valid for some sensor applications. Then you have to rethink about those approximations. So I have mentioned one important approximation is Boltzmann approximation. We have dilution approximation. We have parabolic approximation. Parabolic approximation is something related to density of states, where we have considered the nature of the states as parabolic, if you remember. If you don't remember, again you can go back and check the lecture. So these are some of the important approximations. However, today we will discuss some approximations associated with device analysis. So I have mentioned here a few. For example, space charge neutrality. So we will consider space charge neutrality when we consider device, a particular device. We will consider depletion approximation here. We will consider charge sheet approximation, and we will consider gradual channel approximation. So all these approximations will be discussed in this particular lecture, and we will learn how these approximations are taken into consideration, why they are taken into consideration, and when they should be taken into consideration. So with this, let us start the lecture and see each of these topics one after another. So we already have discussed different approximations related to device analysis. However, there are few more approximations that we need to learn before we go into the device analysis part. And to begin with, let us see what is the approximation related to the space charge. So the first approximation, which is related to space charge, is known as space charge neutrality, wherein we consider the rho is equal to 0. That means the space charge concentration is equal to 0. And if you consider rho is equal to 0, the Gauss law or the equation associated with Gauss law will become or will reduce to dE by dx is equal to 0 for 1D condition. In this case, let us consider only 1D situation. So in such a situation, your Gauss law will be equal to 0 because your rho is equal to 0 under space charge neutrality approximation. And what is the physical significance of that? The physical significance of that is your electric field will be constant with respect to x, because your d by dx is equal to 0. So in many cases, you will find that people consider quasi-neutrality condition. So in quasi-neutrality, what you do is you consider rho to be approximately equal to 0 and not exactly equal to 0. So in quasi-neutrality condition, you consider that the value of rho is very, very small and is approximately equal to 0. And in such a case, you also have the concentration del n to be equal to del p, approximately equal to del p. So the excess carrier's concentration also is approximately equal for both electrons and holes. So when you consider your del p and del n both are equal, this particular relation signifies that your del p and del n both are very, very high compared to the difference between them, as said over here. Okay, so individually your del p and del n both can be very high, but their difference should be very small. That is what this particular approximation signifies, right? So individually they can be very high, but their difference should be very small. Now the advantage of this space charge neutrality is, as your del dE by dx is approximately equal to 0 or equal to 0, you don't need to solve the Gauss law equation in the device analysis. So you are, in this case, solving effectively 4 equations. Apart from that, as your del p and del n both are approximately equal, so you can only solve for either del n or del p. So you don't need to solve the equations for both del n and del p, rather you solve only for del p or del n, because both of them are equal. So the effective equations that you need to solve will further reduce to 2, because you don't solve the Gauss law equation, and out of the rest 4 of the equations you only solve a pair, either for del n or del p. So effectively you are solving only 2 equations in the device analysis. So this is one of the advantages that you get once you consider space charge neutrality. Another approximation which is related to space charge is known as depletion approximation. So in depletion approximation, what you take is the space charge concentration is approximately equal to Q into Nd minus Na. That is, you consider that the free charge concentration is very, very low. So we know that rho is equal to Q into Nd plus P minus Na minus N. So in this equation, your P minus N term is much lower than Nd plus minus Na minus term. This P and N individually can be very high, but their difference should be very, very small. That is, the magnitude of P minus N should be very, very less than the difference between Nd plus minus Na minus. So this will lead to an equation which is this one, Q into Nd plus minus Na minus. Now this particular approximation is very useful in analyzing the space charge in a junction. For example, say PN junction. So once we go into the device analysis in details, you will find that depletion approximation is very useful. And another term associated with this approximation is known as Debye length. So in order to explain the Debye length, let us consider the equation associated with rho for n-type semiconductor. So for n-type semiconductor, the equation of rho will be approximately Q into Nd plus, because your Na plus will not be there. It's an n-type semiconductor, so the equation will be rho is approximately equal to Q into Nd plus. Okay, under depletion approximation. Now, if you write the Gauss law for 1D condition, then your del E by del X will be approximately equal to Qnd plus divided by epsilon for 1D. That is one dimensional consideration. Now let us replace the value of E with minus d psi by dx that we already have explained in our previous lecture. So the equation will become d squared psi divided by dx square is approximately equal to minus Qnd plus by epsilon. So this is the equation that you will get. Now we can rewrite this particular expression the way it is written over here. We have just multiplied the thermal voltage in both numerator and denominator. Then this particular term will have a dimension equal to 1 by length square. If you figure out the dimension of this, you can do this in your home. You will find that the dimension is equivalent to 1 by length square. So this particular equation will reduce to Vt by Ld square. Here this Ld is known as Debye length. This particular term Ld is known as Debye length, and this Ld, the expression for the Ld can be given as root over epsilon Vt by Q Nd plus. From this equation, if you calculate the value of Ld, then you will find, so you just replace this particular value in this equation, and then you will find that the expression for Ld is equal to root over epsilon Vt by Qnd plus. Now this Debye length signifies how the potential varies with distance, right? So if you look at this d square psi by dx square, then the value of Ld will signify how the potential psi varies with distance. So this is the physical significance of Debye length. Now apart from these approximations, there are two more approximations. One is known as charge sheet approximation and another one is gradual channel approximation. In case of charge sheet approximation, what we assume is, for example, if there is a semiconductor block and if there is some electric field in the surface area, you will find a lot of electrical charges are accumulating near the surface. And in such a situation, we can consider this particular accumulation as a sheet of charge, as if this is a charge sheet. So under the influence of electric field, the charges, that is electron, will accumulate near the surface, and we can assume this particular accumulation of charge as a charge sheet. This is what charge sheet approximation is all about. However, in practice, you will find that the concentration of charge is varying with the distance. However, if you consider only the surface or very less depth from the surface, you can approximate this particular situation as a charge sheet. So during the MOS analysis, that is metal oxide semiconductor analysis, this type of approximation will be used, and we'll be discuss this in details. So this is what is known as charge sheet approximation. And if you look into the gradual channel approximation, this particular approximation helps us to reduce a two-dimensional situation into a one-dimensional situation. For example, if you consider a two-dimensional situation for a Gauss law, then you can write del Ex by del X plus del Ey by del Y is equal to rho by epsilon. However, if in any case you find the X component associated with the Gauss law is much less than the Y component, then this particular equation can be approximated as del Ey by del Y is approximately equal to rho by epsilon. So your two-dimensional situation can be reduced to one-dimensional situation. If we can assume, or if the situation is something like this, where X component is much less than the Y component. So again, one thing you should observe in this case is, this term is not necessarily the electric field. This is the change in electric field with respect to X. So individual Ex and Ey can be higher. But if the change with respect to X is significantly less than the Y component, then you can reduce this particular equation into one-dimensional situation. So this is known as gradual channel approximation. So you'll find during device analysis, all these approximations are not applicable in many cases, and hence you'll find there is an approach towards analyzing the device. So the approach in device analysis that we generally follow is given here. So we follow these 3 points, wherein first we divide the entire device into different zones. For example, if you consider a PN junction, we can divide this entire PN junction into 2 different zones. One is the near junction area, which is known as space charge region, and the other is the rest of the area, which is also known as neutral or quasi-neutral regions. After dividing the entire device into different zones, we analyze the zones or regions independently for 5 different parameters, that is N, P, Jn, Jp and E, using suitable equations and boundary conditions. So we solve for these 5 different parameters. Once we solve these 5 different parameters, or we analyze these 5 different parameters in different zones, what we do is we combine them to get the final result for the entire device. And in this combining process, we ensure that the continuity of the parameters are maintained. This is the in general practice of analyzing a device in semiconductor physics.
So we already have discussed approximations associated with device analysis, and specifically we also have said that there are 4 different approximations that we will consider. One is space charge neutrality, one is depletion approximation, one is charge sheet approximation, where once there is a a particular charge that accumulates in one of the surfaces, we consider this as a sheet of charge. So similar type of approximation. And one is very important, which is gradual channel approximation. So all these approximations you need to remember when we discuss about a particular device, or when we explain the working of a particular device, because these approximations in some cases may not be valid. If you develop a sensor, there is a possibility that these approximations will not be valid, and then you have to bring that into your analysis in order to get a in order to get a correct explanation or correct expression. Okay. So nevertheless, we will discuss different devices first with these approximations, and we'll try to understand how we analyze the conventional devices, and then we will also see what are the different types of sensors that one can build using those devices. We will also show some of the experiments associated with them. So let us conclude this lecture today. We will meet again in the next lecture with new topics. Thank you.